Question 1. For each of the following media, determine whether they store waveforms in an analog or in a digital form. We'll start off with a cassette tape, not a very common form of storage these days. In fact, it's quite outdated, so we know that it must be an analog form of storage. How about B, a floppy disk? Now, once again, this is quite an old form of storage, and just like the cassette tape, it uses magnetic fields in order to store data. But hang on, floppy disks are used in computers, and computers can't process analog information. So the floppy disk must be a digital storage medium. How about a USB flash drive? Well, this one's much more modern. In this case, even though we can store things that look like analog sound signals, the analog sound signals are in fact digitized. USB flash drives are used in computers, and computers can only process digital data. So they must be a digital storage medium. Finally, what about a vinyl record, like the LP record I showed you earlier? This is of course one of the older forms of storage. It's hardly used anymore, and it stores musical information. It's not used in a computer. Data on it is translated directly to a loudspeaker, which reproduces the wave on the record itself. And so the wave must be in an analog form. We don't need to worry about interpreting ones and zeros and then processing them into a sound wave. Instead, we just read straight from the record. Question 2. Given the original waveform, up here on the left, which digital recording has the highest fidelity out of these three choices below? Can you remember what fidelity is? It's simply a measurement of how accurate the waveform is to the original version. So we talk about the fidelity of a copy or of a record of some original sound wave. So here's the original sound wave that we have, just a simple sine wave, and we're trying to figure out which one of these is the best copy of it. So we can see that the one on the right is very jagged. We don't sample it extremely often, and we can only take about 3 or 4 different values that aren't 0. We've got 1, 2 above 0 and 1, 2 below 0. So this means that we're not using a 16-digit binary number to encode it. We might only be using a 4-digit binary number. Here we have many more different numbers that we can take on. We have 1, 2, 3, 4, 5, 6, 7, around 10. So this is higher fidelity than our rightmost option. If we look at the leftmost one though, the sampling rate is closer together, and we can have even more different values for the height of the wave. Even if we're not looking at the sampling rate or the encoding, we can still see that our original shape looks most similar to this leftmost shape. So this is the correct answer. The leftmost shape has higher fidelity than either of the other two shapes, because it's most similar to the original version. Question 3. What base 10 numbers are represented by the following binary numbers? We'll start off with 1000. Now, when we're using base 10 numbers, we talk about the columns for each digit. We have the ones column, the tens column, the hundreds column, and the thousands column, right? In base 2, the numbers look just the same, except this is not 10, this is 10 base 2, which is going to be a 2. So our columns end up being 1s, increased by a factor of 2, 2s, increased by a factor of 2, 4s, increased by a factor of 2, and 8s. So let's look at our example here, 1000. In this case, we have no units, no 2s, no 4s, and 1 8. So what's this number going to be? It is, of course, just 8. That makes sense, right? All right, let's go on to a different number. 0110. So once again, we have the 8s column, the 4s column, the 2s column, and the 1s column. So how many 8s do we have? Well, 0. How many 4s do we have? 1. How many 2s do we have? Also 1. How many 1s do we have? None. So add them up, and we'll get 6. Finally, what is 1011? So in this case, we do have an 8 in the first column. We have no 4s. We have a 2, and we have a 1. So add them all together, and we get 11. Remember that just like we can represent any number we want with base 10, it's possible to represent any number we want with base 2, or indeed any base greater than 2. Question 4. Give an advantage and a disadvantage of high-fidelity sound recordings. Alright, well, what's an advantage first of all? Why would you want a hi-fi system? Well, the answer is because the sound recording quality is much better. If we have a very high-fidelity sound recording, or a very high-fidelity sound reproduction, then we're hearing the reproduced sound as an almost exact copy of the original sound. So it means that high-fidelity sound recordings are more accurate a copy. But hang on, if we want nice, good, accurate sound recordings, then what could possibly be a disadvantage to having a high-fidelity sound recording? Well, the answer here is of course to do with the amount of data it takes to store a high-fidelity recording. If we digitize a high-fidelity recording, then we're going to have a huge number of samples and a huge number of different values for each sample. This means that we have a lot of data, and that means that if we want to send it anywhere, or if we want to store it on a CD or a DVD, it's going to take up a lot of space as data. And so if we want to store anything else in that CD, we might not have enough room. It is possible, even if we have a high-fidelity recording, to compress it using particular computer algorithms. And so that might look like a zip file or an MP3 recording. Both of these, though, will remove a small amount of the data in order to compress it better. So although it is possible to fit a lot of, for example, MP3 files on a CD and only a small number of raw wave data, the MP3 recordings won't be quite as high quality as the raw wave data. Question 5. Explain the relationship between sampling rate and fidelity. Can you figure this one out? It shouldn't be too hard. The fidelity of a recording is a measure of how many segments we split it into, or rather how closely it mimics the original sound, whereas the sampling rates are how often we split a recording per second. Can we see that there's going to be a relationship between the number of splits and the fidelity of the recording? Remember that if we want high fidelity, we need to mimic almost exactly the original sound. But if we're only taking a couple of samples per second, we can't really do that. So if we want to make a high fidelity recording, we're going to need lots of samples. So when an analog waveform is digitized, it is divided. We of course have to take the amplitude of the wave and store that digitally as well. But if we take more samples, then we can have thinner chunks of digitized data. And that means that when we put them all together, it'll look very, very similar to the original waveform. If we only take a few samples per second, then the waveform we end up with will be very, very chunky and very, very dissimilar to the original recording. So for this reason, if we have a higher sampling rate, we also have higher fidelity. So that's the end of the questions. We've talked a bit about the relationship between sampling and fidelity and exactly what those terms mean. We've also talked about how we can transfer an analog signal into a digital signal.